Homework 13, the rational zero theorem, video 2. In the previous video, we looked at a specific example of zeros of a polynomial function and tried to push them back up through the work to see where they were embedded in the original function. What we were basically doing was discovering something called the rational zero theorem. In future videos, I will abbreviate rational zero theorem RZT. And the rational zero theorem goes something like this. If f of x is a polynomial function, and notice I didn't represent all of it. I only represented the leading term, which generically we called a sub n times x to the n power, and I only represented the constant term, which we're representing as a sub 0. Just remember that the subscripts match the number of x's attached to that coefficient. So this coefficient belongs to x to the n. This coefficient has no x's at all. But those are the only numbers we needed. Recall in the previous video, a lot of the zeros were embedded in the 18 at the end, and the denominator of 2 was embedded in the leading coefficient. But let's continue. If f of x is a polynomial function with integer coefficients, meaning that none of the coefficients can be decimals, none of them can be fractions, they have to be positive or negative whole numbers. So that's nice. And x equals p over q, some fraction. Now, by the way, this could be a whole number if the denominator were 1. So this includes the possibility of x being a whole number. But if x equals p over q is a rational zero of f of x, rational just meaning a ratio of whole numbers, then p is a factor of a0 and q is a factor of an. Let me translate that. The top is a factor of the constant being the number at the end of the polynomial. Your numerators, I should say, your denominators have to be a factor of the leading coefficient. Remember, we abbreviate that capital LC. So any rational zero, any whole number or fraction or ratio of whole numbers that make this function equal to 0 must be of the form factor of the last number on top of factor of the first number. So how can this help us? Well, let's go back to the function that we saw previously. F of x equals 2x to the third power minus 13x squared plus 27x minus 18. And let's say I was going to ask you to find the zeros without giving you the hint that I gave you in the previous video. In order to not just guess numbers at random and hope to get lucky, we need to narrow our guesses down. What this says is our guesses for rational zeros, in other words, our guesses for either whole numbers or fractions that make this equal to 0, must look like a ratio where the top of the ratio, the numerator, is a factor of the constant term, the number at the end, and the denominator of those ratios must be factors of the leading coefficient. So for this problem, instead of actually finding the zeros, which we had already found previously, let's just list the possible rational zeros. And I'm going to be using that phrase quite a bit, so I'm going to abbreviate that PRZ. So PRZ is possible rational zeros. RZT is rational zero theorem, the name of this statement. How do you list the possible rational zeros? Well, according to the rational zero theorem, the only possible numerators are factors of the constant term, and the constant term here is negative 18. So our numerator must be a factor of negative 18. The rational zero theorem also states that for your possible rational zeros, the denominator must be a factor of the leading coefficient. The leading coefficient here is 2. So the denominator must be a factor of 2. So let's list all the possible factors in the numerator and all the possible factors in the denominator. So what can you multiply by to get 18? Well, you can do 1 times 18. You can do 2 times 9, or you could do 3 times 6. Those are our only possible factors of 18. You could put them in order if you wanted to, or you can put them in pairs like I did, or you can do both. Start with the smallest possible factor and its cofactor. 1 times 18 is 18. The next smallest possible factor, 2, and its cofactor 9. 2 times 9 is 18. The next smallest possible factor, in this case 3, and then 3 times 6 is 18. Normally you would try 4, but 4 is not a factor of 18. Then you would try 5. 5 is not a factor of 18. But then when you get to 6, you're starting to repeat yourself. And if you're thinking, wait a minute, those all multiply to give 18, not negative 18, don't worry, I'm going to take care of that in just a moment. These numbers, however, still are all factors of 18. What about factors of 2? That's easy. 1 is a factor, and its cofactor is 2, because 1 times 2 is 2. Now, what about the negatives? Well, when you're listing your factors, you can start by just listing the positive ones, and then keep in mind that all of the negative counterparts are also factors. And a real easy way to capture all the positives and negatives is to just stick a giant plus minus in front of this fraction. Now, this isn't a number, this is a bunch of numbers that we're going to create. How are we going to create them? The way you list your possible rational zeros is you make every possible fraction that you can. Make every possible fraction by picking one numerator and one denominator. Now, what I recommend is to pick one denominator and then go through all the numerators. For example, let's start with the denominator of 1 and list every fraction we can make with the denominator of 1. So plus or minus 1 over 1, that's the first numerator. Plus or minus 2 over 1, 18 over 1, in my brain I've already put them in order. That's the second numerator. Plus or minus 2 over 1, that's the third numerator. Plus or minus 9 over 1, that's the fourth numerator. Plus or minus 3 over 1, that's the fifth numerator. And plus or minus 6 over 1, that's the sixth numerator. These are what I casually call my over 1s, because they're all over 1. Now I need to change the denominator and write all of my over 2s. Well, same thing. We're just going to write 6 fractions with these numerators, except this time we'll put them over 2, all with a plus minus. So plus or minus 1 over 2, plus or minus 18 over 2, plus or minus 2 over 2, plus or minus 9 over 2, plus or minus 3 over 2, plus or minus 6 over 2. And I know what you're thinking, this is a lot to write down. Well, you're right, but it's very methodical and systematic. These are my over 2s. So I would rather do something that takes longer, but I can just go through it and do it, than something that doesn't take too long and I have to dwell on it forever. Now, when you create this list by splitting off all of your possible fractions, you will get several fractions that can reduce, not the least of which are all of my over 1s. And honestly, when I'm writing my over 1s, I'm thinking, I don't need to put 1 on the bottom of this fraction, it's a whole number. So if you want to be a little more expeditious in making your list, when you write your over 1s, don't literally write them over 1. Plus or minus 1, plus or minus 18, plus or minus 2, plus or minus 9, plus or minus 3, plus or minus 6. For all of the other fractions, there's the possibility that some of them will reduce, some of them won't. For example, in my over 2s, the first fraction is plus or minus 1/2. That won't reduce. But the next fraction is plus or minus 18 over 2. That does reduce to plus or minus 9. Here's a handy rule of thumb. In your list of possible rational zeros, if you set up a fraction that reduces, you can just throw it away, because it will reduce to something else that is already in the list. So 18 over 2 reduces to 9, and that's already listed. 2 over 2 reduces to 1, that's already listed. 9 over 2, that won't reduce, so it's my next fraction. Plus or minus 3 over 2, that won't reduce, so it's next to my list. But plus or minus 6 over 2 does reduce, so it's gone. So that's another thing you can do to save some time. When you're making your list of possible rational zeros, for your over 1s, don't actually write the over 1 part, just write the numerator. But for every other fraction, before you write it down, ask yourself, will this reduce? Because if it will, don't write it, it's represented elsewhere. And in fact, if you do that, you can write it in one fell swoop. So this list, as long as it is, these are the only rational numbers, the only whole numbers or ratio of whole numbers that could possibly make that function equal to 0. How many are in this list? 2, 4, 6, 8, 10, 12, 14, 16, 18. So it's only 18 numbers, some of which might make this equal to 0. Now there's something that I need to point out. There are no guarantees that any of these will make this equal to 0. The only guarantee we have is if there is a whole number that makes this function equal to 0, or a fraction, a ratio of whole numbers that makes this equal to 0, it is in this list. So for example, don't try 5. There's no way 5 will make this equal to 0, it's not in this list. 6 could make it equal to 0, so could negative 6. 7, nope. 1 or negative 1, yes. So that's all this is. This is a list of candidates of numbers that might make this equal to 0. There's no guarantee which one will, if any. It is possible that a function can have no rational zeros. They could be things like the square root of 2 or 3 times the square root of 7, which are not in this list. Those are irrational numbers. This is our possible rational zeros. So how do we take advantage of this? Well, I'll show you a complete example in the next video, but just to put some closure and connect this back to the previous example in the first video, we found the zeros of this function already. I gave you a hint that one of them was 2, but do you recall what the zeros were? One of them was 2, one of them was 3, but the other one was 3 halves. So we already know what those zeros are. And if you'll notice, there's 2, the plus part of that, there's 3, the plus part of that, and there's 3 halves, the plus part of that. So all of our zeros were rational, and they were all included in this list like they were supposed to. So how does this list help us find zeros? I'll show you in the next video.